All right. Well, hello, everybody. Thank you so much for joining and for giving me and Damien, who lead the Microsoft Azure HPC Solutions for the Americas, an opportunity to discuss how Azure can provide great value for your HPC needs. Azure is at the forefront of innovation, but this innovation can come at a substantial cost. Traditionally, customers have invested tens of millions of dollars in specialized and highly tuned infrastructure to tackle their business critical needs, and the investments are most often made in an on-premises infrastructure. Today, Damien and I will discuss the benefits of running HPC in Azure Cloud with examples from several clients for different types of HPC workloads and a discussion of how Azure is developed to especially enable HPC. Before digging into the question of on-premise high-performance computing or cloud high-performance computing and which is better, it's useful to review how and why high-performance computing came about. HPC has been driven over time by the need for faster and more powerful computing to solve critical, often global problems. Starting over here in the upper left, the first computer capable of HPC was the ENIAC at the University of Pennsylvania, and Penn is my alma mater. In 1943, standing for the Electronic and Numerical Integrated Computer, it was developed because of World War II military needs, such as calculating artillery firing tables, and later during the war used for code breaking. After World War II ended, it continued to be used for Cold War design of nuclear weapons, submarines, and aircrafts, and for intelligence gathering and processing. Jumping ahead a couple of decades to 1964, CDC, or Controlled Data Corporation, put out the first computer, which was called a supercomputer. It started with 500 kiloflops and up to 1 megaflops, designed by Seymour Cray and others. As I'm sure you know, Seymour Cray went on to form Cray Research, and in the 70s and 80s pushed the performance to more than 100 megaflops and then to gigaflops with multiple processors. As a point of reference, a modern desktop computer has performance in the range of hundreds of gigaflops to tens of teraflops. We're now in petaflop computing, and 100 petaflops is 100 quadrillion flops, or floating point operations per second. So moving along in the timeline, in the 1990s, looking right here, the Japanese dominated the supercomputer market. They had uses ranging from aerospace research over in Japan to nuclear weapons research for the US Department of Energy here with Sandia National Labs, which could not be conducted without HPC. ASCII Red was the first computer built under the Accelerated Strategic Computing Initiative, ASCII, the supercomputing initiative that the US government created to help the maintenance of the US nuclear arsenal after a 1992 moratorium on nuclear testing. So they had to do simulated testing. The goal was to build a teraflops machine, so we're going from peta to tera, that could do nuclear detonation simulation. It was built by Intel and installed at the Department of Energy Sandia National Lab in 1996. This machine remained the world's fastest supercomputer until late 2000. Now, during the 2000s, rather than increase processor speeds, focus was on increasing the number of processor cores. This led to hybrid clusters with a large number of processors, each with a small number of core sharing RAM and some cache space. Climate research, which we talk about a lot nowadays, was enabled by HPC in 2004 with the Earth Simulator Center, and it had almost 36 teraflops. Petascale computing became a reality with the 2008 launch of the Roadrunner machine at Los Alamos National Lab, another Department of Energy national lab. It was the world's first HP system to hit 1.026 petaflops, which is 1,000 million, 10 to the 15 floating point operations per second. By 2018, 10 years later, we were above 100 petaflops with a supercomputer built once again for DOE for the Oak Ridge National Lab. The Oak Ridge National Lab computational scientists do research in everything from COVID-19 pandemic modeling to global weather and climate simulations, to high fidelity simulation for next-gen nuclear reactors, and a whole lot of other stuff. Which takes us to present time. In 2020, just last year, Azure Cloud became the first cloud HPC to make the Graph 500 list in the top 20. And today, HPC today, this year, 2021, Azure took HPC on demand in public cloud to a new level. We delivered 16.9 petaflops on the HPL benchmark, known as LINPACK. This resulted in Azure taking 4 consecutive spots from number 26 to number 29 on the top 500 list. And we have a supercomputer available on demand for HPC in 4 global regions now. With Azure Cloud Computing, as an addition to on-prem high-performance computing, and with the cloud computing comparing favorably with performance of on-prem supercomputers, new horizons are open for businesses, academia, and government for reasons that I'll talk about. So Microsoft can help your organization solve problems faster or solve problems that might not otherwise be able to solve. And let's take a look at cloud versus HPC and what you might do that. The barrier to entry can be the infrastructure costs, but then when you get into operations, there's the cost of your infrastructure and capacity or not having enough capacity. If you take a look at this graph, on-prem HPC on the left is fixed infrastructure. And I think you're all in the IT world. You understand that fixed infrastructure has its advantages and disadvantages. It is certainly for HPC challenging in terms of both time and money to expand capacity, especially nowadays with our current issues of supply chain delays and chip shortages. If you look at the graph, everything that is below the bar represents capacity that is paid for but not used. And then everything above the bar represents capacity that was desired but not available. If it wasn't available, that means that engineers couldn't do simulations for automotive crash testing, or for testing out self-driving vehicles, or for chip design. It means that researchers couldn't run their workloads. It means that movie studios couldn't render images into film on deadline, as just a few examples. With on-prem HPC, organizations, your organizations, might also be challenged to collaborate between departments and between global locations, because traditionally HPC environments, HPC infrastructure is siloed and typically not run by central IT. It's run by different departments. Moving over to the right, a cloud platform by definition is the only place where you can take advantage of true elasticity over massive compute scale. With cloud-based HPC on Azure, you'll get infrastructure built especially for HPC, a real differentiator for Azure and why we're on these lists. You can scale up or down your resources as you need. You can overlay intelligent analytics, and the power of HPC plus AI is amazing. We'll have a couple of examples. You can choose to keep your on-prem HPC and burst into the cloud as you need more capacity for these what's typically inconsistent demand spikes. Or if you're a newbie to HPC, or you just want to get out of the HPC IT business, you might choose to migrate completely and build a cloud-native model for HPC. When you use Azure HPC, there is no unused infrastructure. Usage mirrors demand in a one-to-one relationship, maximizing the resources for the work that needs to be done. Now let's go ahead and take a look at some real-life examples of customers using Azure Cloud for their HPC needs. The first example is in the energy industry. Repsol is a global energy company based in Madrid, Spain, but operating all over the world. They wanted to modernize their G&G, geological and geophysical applications used for exploration. They do both downstream and upstream energy work, but this was really all around downstream exploration. This was part of a cloud-first initiative by the CIO to reduce costs, streamline operations, and enable better collaboration. Things that you always think about when you think about the benefits of going to cloud. It's true for HPC as well. When it came to HPC, Repsol was finding it difficult to scale up or down using their on-prem infrastructure. In addition, their teams, who were spread around the globe, could not collaborate on the same seismic project because HPC was being done in local data centers. So they could get on a plane and go to a local data center, or they could just continue to be siloed. As an additional challenge, oil and gas reservoir simulation has massive amounts of data, tens of thousands of petabytes. And to avoid disruption, this data needed to be migrated quickly and accurately. Microsoft solved these problems by developing, testing, and executing a solution with its partners for data management and with the ISV partners whose simulation software Repsol used. So while some people build their own HPC software for things like modeling and simulation, there are a ton of ISV vendors out there who have already built this software, which customers use. And to date, most of it's been sitting on-prem, but we're working with customers here at Microsoft Azure to port those solutions to run on Azure Cloud so that we have benchmarks and we've already worked out integration challenges. The end results for Repsol were better performance, lower cost, improved compute, and improved storage capacity. All great things. In addition, they had a more efficient operational model that didn't require local teams to manage HPC infrastructure all over the world, which let Repsol focus more on the business of oil and gas and less on the business of maintaining IT. Finally, with their data sitting in the cloud, geographically dispersed teams who were actually doing the simulation were able to collaborate for the first time without traveling to another part of the world. So I'm not sure if there's any oil and gas or energy folks out there, but hopefully this is an interesting example for you. Modeling and simulation is used in a lot of different sectors, not just energy, and you can imagine similar benefits for you if you're in a different sector. So moving to something completely different, switching gears, let's take a look at the world of Formula One racing. For those of you who don't follow F1, this is a series of races each year, which is run around the globe. The last race was in Turkey 2 weeks ago, and this weekend they're racing in Austin, Texas, which is new for a few years that an F1 race is being run in the US. Alpine Renault has two great racers, Fernando Alonso and Esteban Ocon, who you may have heard of because their photos get thrown all over social media. However, with cars reaching 220 miles per hour, F1 racing is not just about the driver. It's about the car and adapting the car in race weekend and between races. Often the races are from one weekend to another weekend, so they can occur pretty fast and they're going to be in different countries. Alpine Renault builds its cars especially for the races, and they rework the cars with a focus on aerodynamics and gearing between races based on performance to date, conditions of each track in the different locations, and what the competing teams are up to. If you can believe it, there are 20,000 parts per car. So it takes a massive amount of data to determine what modifications to make to give them an edge in racing. Because Formula One limits actual test runs and wind tunnel hours, computer simulation is critical to gaining an edge in performance. There's test drives on Friday, on Saturdays qualifying, and on Sundays the race. And then they put engineers out with each team in the field at the racetrack globally. And then back home, they're running simulations of everything that's happening on the track at the same time. So this is generating massive amounts of data. In addition, the team, if races are week to week, back to back on weekends, the team only has days to design, test, and manufacture, and then ship the new parts. So Microsoft worked with Alpine Renault to have them run their simulations in Azure Cloud so that they could use the technology to gain a competitive edge. They overlaid Azure ML to analyze 30 to 50 billion data points per race weekend, and then multiply that over weeks and weeks and weeks. These data points collected throughout the season, and then they continue to run analytics on this ever-increasing amount of data to determine, do we change this flap here for aerodynamics? Do we change that gear? It's all about keeping the race car on the track and the driver safe, but beating the other cars, of course. With this HPC plus AI solution, Alpine Renault can now run thousands of simulations cost effectively. Compare that with the 90 or so simulations that they used to be able to run, so thousands versus 90. Additionally, what took them hours to run can now be run in seconds, which is why they can do this cost effectively. And engineers have the anomalies identified by ML for them. Remember, I said 30 to 50 billion data points per race weekend, and those race weekends occur over an entire season. So now the engineers can spend their time on innovations and changes that they want to make to the race car rather than on parsing data. That was my second example. Let's go ahead and move to Damien. He has a couple of other client use cases for you, and then he's going to dive into some of the technical differentiators of Azure HPC, and we'll leave some time at the end for questions and answers. Damien?
All right, very good. Thank you, Desiree. If you would kindly advance to the next slide. Pick two more use cases we wanted to cover today, and I'm always humbled by the impact and broad reach of HPC applications and workflow. And one I wanted to pick and go a little deeper on was the ventilator splitting project that we worked on with Duke University. I mean, as everybody knows, ventilators were and have been a scarce resource through the pandemic, and the team at Duke University was really urgently looking for a way to safely and effectively split a single ventilator between two patients. Previously, for a shared ventilator to work, patients across two patients, they needed, amongst a number of other factors, to be approximately the same weight, have similar lung compliance and capacity. And finding two similar patients in one hospital ward can be pretty much a game of chance. Think of two balloons, one with a thick wall, one with a thin wall. If you try to inflate both with the same level of effort or pressure, the thin wall balloon is going to get much larger. So same challenge presents itself with the patient's lungs. Desiree, are you still presenting? I think on my side it might have fallen off.
I am. Did it disappear? Let me just see what's going on.
So one solution, thank you, is to find a way to tailor the airflow for each patient without having to rely on the ventilator to do all the heavy lifting. So to this end, Duke partnered with Microsoft for AI Health to run over 800,000 compute hours in just 3 days to build the solution. And if you're not familiar with the Microsoft for AI for Health program, it's a $60 million 5-year program to empower researchers and organizations with AI needs to improve the health of people and communities around the world. And so the goal of Duke's work was to provide physicians with the entire parameter space so that no matter what patient weight or lung capacity they went into, that data was already there and would be pre-computed and give them the guidance they need to determine how best to use that splitter. So they took roughly 100 terabytes of computational data and shipped that over to Azure for 3 days, and we distilled that down into just a handful of gigabytes that can then be shoveled over to a mobile application. So the clinicians simply put in the required data about their patients and ventilators, and the app is already there to spit out the best combination of resistors to use to ensure that both patients are receiving the correct amount and personally tailored amount of air. And because the calculations have already been done, the response is immediate. And because the app is always pulling that data down from the cloud, it's able to be updated dynamically as more data becomes available and as we get feedback back into the system. So very cool, very impactful project, and it was very, again, humbling to be able to serve the community in that way. And much like Desiree, I'm going to flip to a use case which is completely different, but also has a bit of a spin on it from the last 2 years. So if you haven't heard of Jellyfish Pictures, they're an animation and visual effects studio who've been recognized with an Emmy, British Academy Film Award, 2 Visual Effects Society Awards, and I believe they worked on the last 3 Star Wars films. They provided some visual effects for The Watchmen, Train Your Dragon, and so on. And so over the last 20 or so months, Jellyfish was looking at a pretty dynamic landscape of remote artists and unpredictable IT requirements and really demanding project deadlines. And so over the last 20 months, Jellyfish had hired roughly 200 people from 20 different countries. And the problem is how do we adequately serve all 200 artists with the right amount of compute and locality with the data and so on. And so they adopted a global compute footprint within Azure, stretching across Ireland, Netherlands, and the United States. And so they were then able to augment their existing infrastructure with spiking up to 90,000 additional CPU cores, which is roughly a 70% boost over the on-premises capacity. And again, no impact to their existing pipeline of work, gives their users and their employees the ability to work from anywhere. So no matter where the creatives are based, they can sign on, get access to the infrastructure, just like they were at the studio. And I'll also add, it's important to note that it was not a complete lift and shift from a storage context. All assets, all visual effects assets remained on premises, aside from edge caching within their Azure resource groups. So no need for them to copy entire volumes. The compute was driving the pinned locality, and the output continues to be written back on premises as well. So massive augmentation to available resources without a fundamental shift in their workflow either. So looking ahead, Jellyfish is now also looking to, oh, sorry, just one more quick there on Desiree, just a couple more sentences, to augment, again, with bringing additional GPUs online for additional virtual workstations and enrich their existing data footprint with Azure ML technologies and just go through and mine the data through reporting. So they continue to evolve and take a step closer to an entire digital studio in the cloud. All right. Mindful of time, so let's go to the next slide. And wanted to take, have a few slides, so I'll step through them quickly, but I want to take some time to now at least describe some of the building blocks which constitute the Azure HPC ecosystem. So you go to slide number 10, as we've kind of hinted, there's many different flavors and many different incarnations of a cloud adoption. Very, very rarely do users jump straight into a cloud, and it's a wide spectrum of possibilities. So the way that Azure is configured to not have just one size and support a wide variety of compute workloads across cloud native, across a hybrid architecture, net new, or in also adopting a straight lift and shift as well. But if you go to the next slide, one thing, if you aren't familiar with HPC, HPC is not a single technology or a single line item. It's really an orchestration of many moving parts across the basic building blocks of compute and networking storage, to software stacks for coordination across batch and cycle cloud, to, as we talked a little bit about with Jellyfish and the F1 team with, augmenting and enriching their data with machine learning. So all of that kind of plays into and constitutes a singular HPC solution. And frankly, as technology changes, our definition of an HPC solution also changes as well. But to that end, if we talk about what Azure, next slide please, has provisioned for HPC, we do have a set of compute SKUs, which you can think of in two buckets. One is what we call specialized for HPC. Those are the H and N series SKUs that you see listed in roughly the middle of the screen. Both are connected via InfiniBand, and so they are purpose-built for HPC and HPC plus AML workloads. Underneath the H series VMs, we have several different sub-flavors, if you will, based upon the application needs, be it high memory, footprint, raw memory bandwidth, compute, and similarly for the N series, those are all of our GPU and FPGA SKUs as well. And again, segmented based upon client or application need. General purpose SKUs run across the gamut across our Ds, Es, and Fs, as well as Ls and M series. L being an example of extreme local I/O, M being an example of the need to fill a high memory footprint as well. I think one most common example we have for the M series SKU is in the EDA or silicon design space, where those SKUs will feature up to 2 terabytes of RAM, and if we want to load the entire design and have that local, great, M series is what we want to use there as well. Now, if you go to the next slide, we're just going to have an at-a-glance view across those H series SKUs that I'd mentioned. And HBV3 being our most recent SKU with availability. I believe Azure was to be the first public cloud provider to provide Milan and an available footprint. HBV2 and HB are also AMD-based SKUs with HC and originally H as our original HPC Intel-based SKU as well. But as you can see, all the H series SKUs, what makes them unique within Azure and unique within cloud HPC offerings is they do carry InfiniBand RDMA connections on the back end as well. Same for the N series SKUs on the next slide. Again, we don't try to have one size fits all SKUs. The SKUs are purpose built based upon visualization, appropriately named NV, compute, NC, and also ND for our deep learning and AI functions as well. Let's step through and talk about the other components that can constitute an HPC solution on Azure. This is storage, really. You can think of the four biggest buckets there as bring your own, which is really all the necessary building blocks for a bespoke storage solution, or to enable third storage party providers like Cumulo, Hammerspace, Store1, UDN, just name a few. Azure NetApp Files is a hyperscale configuration of all flash NetApp filers directly connected into the Azure Fabric and managed as a first-party service. So single management pane built into Azure, consume on demand, spin up, spin down storage as needed, and persist back to or cheer to blob for cost optimization as well. Azure HPC Cache is the product we were mentioned back when we were talking about Jellyfish, which enabled them to have that edge caching, or really a mix of heterogeneous storage environments. And of course, you can, if you'd like, you can also have a dedicated Cray system in Azure too. Not listed here are two more storage options, known as Azure Files, which really provides a managed and scalable NFS v4 and SMB file server, and also what we call NFS on Blob, Blob being our object storage, which gives great integration into first-party Azure services and massive throughput, scaling up to terabits a second within a single container. And I'd be remiss if I didn't cover these next two slides real quick, Desiree. One, I do want to ensure that there's some visibility into our partner ecosystem crossing both our ISVs and systems integrators. So we do work very closely with a number of software vendors to ensure that their applications and services are well vetted within Azure. And finally, I do want to touch on one more, saying, last and certainly not least, I'd like to take some time to talk about our people, because our people truly make the difference. And Microsoft has invested, we have decades of HPC expertise, industry expertise, thought leaders and PhDs within their respective field across engineering, business, technical consultants, a dedicated benchmarking team to validate solution scaling within Azure, and dedicated HPC customer support team as well. So the team are certainly super focused on serving customer needs however possible, from architecture definition to algorithm tuning and envisioning commercial goals and outcomes. And so that brings us to our last slide. I think we're right on time. So I would love to hear from you. And please do reach out with any feedback, any comments, any questions. Happy to continue the conversation with you.